do here is talk about calculating that ice jam stage frequency, but I do want to caveat this. We're doing this in 30 minutes, and the statistical theory that goes behind this is pretty extensive and would be a several day course on its own. So I am going to move through this relatively quickly and at a relatively high level. But in the end, if there are specific questions, we can certainly go through them. So I'm just kind of giving you a heads up now that this is not going to cover every aspect of how to do stage frequency, or I guess statistical probability theory in any sort of depth. Okay, so what we'd like you to get out of this particular presentation is first, how do you approach stage frequency when you have observations? I'll give you some guidance from the core, and then what FEMA has available, and then what happens if you don't have observations. And in this case, if you need to use a hydraulic model, again, I'll give you some idea of how we would approach this, and then finally I'll give you an example of statistical tools that you may be interested in. There are quite a few out there, but I'll show you what we use when we are performing these types of analysis. So as Chandler mentioned earlier, EM 1110-2-1612, the ICE engineering manual, it actually does a fairly good job describing how to do ice affected stage frequency. And so I'm going to use that as the basis of this discussion. There are certainly lots of papers and potentially other resources out there, but for us, our engineering manuals are kind of the basis for how we approach things. The data sources that can be used with this sort of analysis, of course, stream gauges. Those are systematic measurements that are always extremely helpful. And if you happen to have a stream gauge near a location where you're doing your analysis, then that's a great way to go. There's also potentially records of events in project offices or district core offices. The state and local water resource agencies, another good source of ice affected stages. In fact, we were just looking at something on the on the Yellowstone River, where the water treatment plant had about 40 years of ice affected stages because of their operations, and that ended up being a really good resource to use. Prior flood insurance studies may contain some information. Historical sort of resources, so that could be the museums, the libraries, newspapers, or books, certainly are things that can at least help understand if an ice jam occurred or ice was present and there was a high stage event, kind of what did that look like, and potentially maybe be able to use that in some sort of quantitative fashion. Interviews with locals, and of course, some of the environmental indicators that we talked about earlier, like tree scars. So when you do have observations, this is what's called the direct approach. And so the way the core terms this is the mixed population frequency curve. And so I'll caveat this, you will see differences in some of these terms, but again, we're using the 1612 terminology here. The mixed population frequency curve, basically, there is no separation in the annual peak stage data. Okay, so it's everything combined regardless of the mechanism that causes that peak stage. In contrast, the combined population frequency is derived from two or more frequency curves. So essentially, you do segregate data based on the actual mechanism that causes that peak stage event. So just to kind of reiterate this, so the mixed population will consider open water, freeze-up jams, solid ice cover breakup. It doesn't matter. It's all combined into one record. And in this case, the use of statistical software to do stage frequency, like if you wanted to perform 17C or just some sort of generalized frequency analysis, there are lots of tools out there, and certainly can help you with this. The combined population frequency analysis, in contrast, would be where you have to dig a little deeper and find out, what events are caused by what sort of mechanism. So you would want to potentially segregate the data into the open water stage, high stage events, freeze up jam. You may even want to go as far as having freeze up and break up jams, and then also maybe look at just what solid ice cover, uh, the peak stages where you had only ice cover but no ice jam present. When you do this combined population frequency analysis, basically at the end, when you have these individual figure out the probabilities of these individual mechanisms, you can then bring them back all together, and that's the equation shown there. And that allows you to have a single probability exceedance based on all these different types of events occurring. So just to kind of illustrate this a little bit further, if you have your combined and mixed curves, oftentimes what will happen is the combined curve will diverge at the tails of your distribution, and those can certainly be ice jams or other events where the peak stage is extremely high, and so being able to account for that is really important when you're trying to make reasonable estimates out on the tails of the distribution. And so when you have your more rare events, it can be really important to get the mechanisms correct on what forced those peak stage events to occur. FEMA also has some guidance on how to use the direct approach. And so I pulled this directly out of this manual. I personally have never used this manual, but I thought for just completeness, we should go through it. And essentially what this is combining the probability of a stage exceedance in any year with the probability of a stage exceedance in the ice jam season. And then basically you're looking at the combined probability of both of these happening. And so I think this is real similar to the way the Corps does it, but they FEMA does use slightly different terminology. So my suggestion is just read carefully and understand the terms, and so you know exactly what what probabilities you're actually calculating with your observations. So what happens when you don't have any sort of observations? And I would say this is likely a more common situation where you're not going to have any records, but you need to do some sort of analysis on what ice-affected stage frequency might be at a certain location. So that for the Corps, we kind of approach it in two different ways. It's kind of the same idea, but looking at two different mechanisms. So if we look at ice jams, so we figure that we want to look and see what an ice jam might do to our stage. What we would likely do is we do this in a Monte Carlo simulation where we would vary the jam characteristics and parameters. And then once we have our ensemble of stages given assumed flow conditions, we could then look at the probability of those flow stages. We can also do this just with ice cover. And so it doesn't necessarily have to be an ice jam. If we want to know what just simply putting ice cover does to the stage in the river, we can do this. We're currently still a little limited in RAS to dynamically grow ice, but we have done some workarounds that seem to be adequate for answering this. And when we say dynamically grow, we mean what happens when the ice grows from the shoreline toward the middle of the river. So your percent coverage of your total river channel changes, as well as when you look at the distribution from upstream to downstream in the reaches that you might consider important. And so that's something that I'll show here in just a second, a study that we completed a couple years ago. When doing this, we would also look at the ice jam database, because this is going to give us information about what type of jam may be present in a general vicinity, So is it a breakup jam that's going to dominate, or can you have both? And that might give us an idea of what we need to look at least in the hydraulic modeling. And then another important aspect of this is we want to estimate the ice cover thickness. So as Chandler just showed you in the last presentation, we could use the AFDD model to get an estimate of what that ice thickness looks like, and that would be one of our primary inputs to the hydraulic modeling. So just an example, if we wanted to do a breakup jam flood estimation, and so we wanted to get the empirical probability of the stage from breakup jam. The first step would be, we first want to know what type of flows may be present, just unimpeded, or flows that would occur without any sort of ice effects. And so that would be something that could be done through a variety of methods, but essentially trying to understand what the peak flow regime looks like. So then we would want to select a range of those flows that we feel are reasonable for the winter time, and then we can use that to evaluate several discharges using solid ice cover or ice jam cases, or both. And from those, we can develop a stage discharge rating curve, essentially trying to understand how the ice cover associated with a certain condition will impact stage at a certain discharge. And then if you're doing an empirical probability, essentially you could rank these and fit a curve, or however you would like to approach that. The analytical methods, obviously, you could use in this case. So if you wanted to fit some sort of analytical distribution, you could do the same once you have the stage discharge rating developed, and you could determine that through the probability of a certain flow. So now you have this as kind of the workflow, but if you wanted to do an example, I did throw this plot in there that's in the ICE manual, the ICE engineering manual. And in this particular plot, what they're doing is developing a compromise curve, which is trying to get the best estimate of what's the probability of stage exceeding a certain level because of jamming, and the probability of stage because of just ice cover. And so this is something that can be really important depending on exactly the mechanisms that you think may be important for your particular reach. If jams are the only thing you're concerned with and ice cover doesn't matter, well then your problem may be even a little bit simpler than what is shown here. So here's an example of how we did. This is ice affected stage with just using ice cover. So the Pend Oreille River in Idaho, it forms ice often, and that ice causes backwater on the power plant facility there at Albany Falls Dam. And what happens is, as the ice extends and thickness increases, that backwater gets, the tailwater basically gets higher, and your net head for generating gets lower, and eventually they have to shut off the units. So we actually went in and used a hydraulic model, used HEC RAS to basically grow ice. So we grew both the transverse ice across the cross section as well as the longitudinal ice upstream to downstream. And then we plotted it there at different flow rates. So you can see that plot at the bottom. And we tried to figure out where the maximum deviations were. And then what this allowed us to do is then figure out a probability of that occurring based on the probability of ice thickness and also the probability of the certain flow rates that we had. And so now Seattle District, who operates this, they actually have a way to figure out the probability that the units may be turned off given certain river ice conditions. Hydraulic modeling is also defined in the FEMA document, and I guess I would point you to the fact that the indirect approach, they do specify several assumptions that are included in this. And these assumptions are certainly related to the ice jam, as far as the frequency of ice jam, and then also the ice thickness, and where they prescriptively define how to find ice thickness to use. And then from there, using the jam characteristics and ice thickness, you can develop a stage discharge relationship using a standard step backwater technique. So very similar to what we were just talking about using HEC RAS. They do actually talk a little bit about grounded jams. While this certainly can happen in nature, we generally don't model those in our for the core, because when a jam gets grounded, essentially a lot of the force balance equation assumptions don't apply, because it's no longer buoyant ice. So we don't often model that, but certainly that's something that could be considered if that's necessary for your project. Here's the combined stage frequency curve specified by the FEMA method. And again, this takes a little bit of studying just to make sure everybody knows the terms and exactly what variables they're using. I think the main thing I wanted to point out here is, and this is spelled out pretty clearly in the FEMA documentation, it assumes that the conditional distribution is the same for peak discharges for all seasons. So essentially, you don't have a situation where your annual peak discharge is always during ice jam season. I think that it makes that assumption that doesn't occur. So please be aware of those assumptions and the terms related to this. And hopefully I think there's a good enough description that hopefully everybody could, work their way through it if they needed to. So what tools do we have for doing statistical analysis? Now, for those that are savvy with different programming languages, there's lots of options. Even just doing some of this in Excel is totally feasible. In the core, we do have our statistical software program, which is SSP, and this is free and downloadable from HEC's website. This can be a really useful tool depending on exactly what you want to do. And I would say that the version 2.2 that they've released just fairly recently has a lot of really nice improvements, especially if you're trying to fit analytical distributions to your data. They also have a lot of lectures and workshop material that will help you learn this particular software if you don't have any experience with it. And so that's one thing that's kind of nice is this particular tool. There is freely available workshops and documentation out there that is pretty extensive. So I think that's certainly one of the advantages of using one of HEC's tools. So in the HEC tool for SSP, they talk about combined population analysis steps. And so these steps generally include visualizing the data, which is always, I think that's a good step for any analysis. You want to look at the flood causational mechanisms for different populations, because essentially the reason for that is that the underlying statistical frequency assumption is that you have independent and identically distributed samples. So whether you're taking a block maxima that is based on an annual period or a seasonal period, if you're violating that independence and identically distributed assumption, then your probability relationship is likely not going to quite be right. And then basically fitting distributions to these samples once you've separated them, and then using the probability of union to then make your final stage frequency curve. So the data visualization tools in HEC SSP, they have the year-over-year plots, which are kind of handy to be able to just look at that. But even more handy is that you can input a daily time series, and you can actually extract the seasonal or annual maximums, as you see in the plot there in the middle. And the time series quilt is not natively available in SSP, but I put that up there as another way to visualize. If you're looking at data that has some sort of seasonality to it, these quilts can be quite effective in trying to understand what seasons are necessary to segregate for your particular effort. So the filtering, again, you can filter by time window or season or duration. You can also filter by a min or max threshold. And this is extremely handy if you are intending to move on to do some sort of peaks over threshold type of analysis. So these sorts of plots are available in SSP. In the newer version, they have some additional plots that I find extremely helpful. They allow you to do a little more QA/QC, and that is you can plot both your CDF and PDF. So basically your different histograms of your data, and look at them and see if there's anything strange going on, or if you have any potential problems with your record. And this is helpful, especially if you are just doing a empirical probability analysis, but I think it also is helpful if you are trying to fit analytical distributions. So the combined population analysis essentially uses that probability of union concept. And so in this case, if you're looking at a stage frequency, you might have we're terming it summer and winter here, but you could have a open water and ice cover situation. And so in many times you'll see differences depending on exactly the river that you're trying to model, or the conditions you're trying to model. And so it's really important to be able to capture both of these and understand the differences between the individual frequency curves as well as the combined population frequency curve. So I'll end it there. I know we're a little ahead of schedule on that, so it leaves some time for questions, but that's okay, because as we get toward the end of the day, it's probably better to be on the early side than run late.